Yeah, so we'll continue discussing online resource allocation for unknown distributions. Good. So, like what we've already talked about is how to handle these known distribution case, but now we have unknown distributions. So the setup is the IID from unknown distributions. First, let me talk about IID more. The main thing what we learned last lecture was how to get something like M over epsilon squared guarantees. M is the number of resources. As long as the budgets are at least M over epsilon squared, we could get a 1 minus epsilon approximation. Now the objective is to improve that dependency on M from linear in M to logarithmic. Okay, good. So at a high level, the intuition is the following, that we want to somehow, there's this dual LP. So like we were learning this M dimensional price. And like the reason we kind of lost linear in M was because we were taking a union bound over this 1 over epsilon to the M, like the epsilon net. So log of 1 over epsilon to the M was losing me this linear in M. And I want to do something better. So at a high level, the reason we'll be able to do this is because it has something strong connections to something called as multiplicative weights or online learning on a simplex. And turns out there you kind of don't have to lose linear in M. You have to just lose logarithmic in M. Okay, so our algorithmic idea would be this following. So earlier we were doing all this like learning based on like, okay, either maybe powers of 2, like, but basically we're taking a union bound over all of these potential prices, 1 over epsilon to the N. Now we'll do something somewhat more naive. The algorithm would be the following. Each time step, I'm going to play a price. Let's say, I mean, in the first round, I just play an arbitrary price. Doesn't matter too much. On average, I have B resources to give. So in any particular time step, I expect roughly B over N of any resource to be. Because in the optimum solution, overall, you'll use B resources. So over N rounds, all of these are IID requests. So any particular time step, I expect B over N resource to be used. So the algorithm would be of the following kind. I'm going to play a price. I'm going to see how much resource is used in this particular round. If, in some sense, you are using more than B over N resource, any resource, the price of that resource should go up. Because I mean, I only wanted to use B over N. If you're using more than B over N, then the price should go up. On the other hand, if you're using less than B over N, then the price should go down. And I want to basically adjust these prices based on this. And the way I'm going to update these prices are using the so-called multiplicative weights. So maybe let's, for simplicity, I'll assume, like just for presentation and make the analysis cleaner, I'll assume the total value of opt. That's the true optimum. Let's say somebody has given to me up, like the total value, like over the entire process, just the value they've given me. They've not told me what is the assignments to be done and what actions are to be taken. The reason you can assume this is because this is just a scalar using like just the first epsilon fraction. It's easy to roughly learn the optimum. So it's without loss of generality. And let's also assume all the budgets are the same. Like there's some large number, some B, because I don't want to carry I don't want to carry this notation J everywhere. So all resources have the same budget. B is roughly, let's say like 1 over epsilon squared. I mean, our bound will be exactly like log M over epsilon squared. That's how my budget will be. So the algorithm will be of the following kind. I'm going to use this multiplicative weights to set prices. Okay, there's some confusion. I think I was just adjusting the slides before. Maybe I skipped one slide. Good. Yeah. So this is the slide. Yeah. So the result we want to prove now is that there is a pricing algorithm that as long as the budgets are roughly log M over epsilon squared, I'm going to get a 1 minus epsilon approximation. And this is based on the multiplicative weights. Some of you might have seen the use of multiplicative weights for offline packing LPs, how to solve packing LPs fast. So it's based on the same intuition. But okay, let's take a detour slightly and what is the setup of multiplicative weights, this online learning setup? So it's basically the experts problem. So you have m experts and you have n rounds. So the setup is you have m experts. Each round, each expert generates some reward between 0 to 1. So in every round, or like maybe the reward is between +1 and -1. So you have n rounds. In each round, each expert generates some reward. But you have to first choose the expert for that round, and then you get to see how much reward they've achieved. So in each round here, your algorithm chooses one of the experts, or maybe a distribution. It could play a randomized expert as well. So this is just a fancy way of saying it's a distribution with some, like over the m coordinates, it sums up to 1. So it belongs to the n-dimensional X simplex. So Al plays one of the experts at random. First, the Al chooses a random expert. Then a random, some reward of each of the experts is written. So Ri is like this m-dimensional vector, which is basically saying the jth coordinate will tell me what is the reward of the jth expert. So each round, Al plays a distribution, and then your reward will be just the dot product. Like if you're basically playing like a single expert, so it will basically be the reward of that expert. So your goal of your algorithm is to maximize the total reward over all the t rounds, over all the n rounds. So is the online learning problem clear? Because I think like 50% of you have not seen it before. So the setup is, it's an online problem. Each round, one thing that's super important is in each round, you have to first choose the expert, and then you get to see how much reward that expert made. The problem becomes trivial if I flip the order. If I had seen in the like ith round how much each expert's value is, and then I choose the expert, then it's a trivial problem. I'll always choose the expert which has the highest value in that round. So the setup is opposite. I first choose the expert, and then I get to see how much reward it makes. But a priori, it would seem like, okay, there's no way I can get the optimum. So that's why I changed the benchmark. The benchmark is the highest reward of an expert chosen fixed expert in hindsight. So at the end of the game, at the end of n rounds, each expert has accumulated some total reward. Like every round, they were accumulating some reward. These m experts. So look at the best of these m experts at the end. Whatever is the total reward of that expert, that's my benchmark. That's what I want to be comparable to. So notice it's not per round whosoever was the highest like reward expert. I'm not summing up the best for each round. The max is like outside the sum. Max is not inside. And the powerful result, the so-called multiplicative weights theorem, is that you can come up with an online algorithm that gets a total algorithm reward is comparable to basically roughly the benchmark, the best fixed in hindsight, up to some think of it like square root n, square root 11 kind of guarantee. So there are n rounds. Naively, you could be like linear in n off, because all these rewards are bounded between ±1. So if you play any dumb algorithm, it could be like linear in off. Each round, it's maybe losing up to a factor, like up to an additive 1 loss. So in n rounds, it would be losing something like order n. But what's nice is that you can actually show that the regret will be something like at most like root n up to some log factors. So benchmark's total value could be like, in fact, you can even do something better than root n. It's actually root of benchmark. Benchmark is at most n. So yeah. So I'm not going to go over the proof of this algorithm, the multiplicative weights, but it's some kind of a exponential way of adjusting distributions overall. Okay, maybe a quick question. Let's give a minute to digest. Like this is actually a very powerful and fundamental result. I made the wrong assumption that by this lecture you would have already seen it. So that's otherwise I would have spent like another 10 extra minutes on this. So it's a very fundamental and powerful result. I would highly encourage all of you who've not seen it before to understand in this in depth. It has many applications, and not just learning applications. For instance, what's one of the reasons I like the result that I'm presenting today is because it kind of connects to historically who were different fields like online algorithms and online learning. This is coming from the learning community, multiplicative weights. Online algorithms is more about competitive analysis. So a priori, the techniques are often different, but this uses multiplicative weights like a tool from online learning as a subroutine to design like a competitive ratio, like for an online problem. And the way we are using it is basically I'm using this online learning algorithm, this multiplicative weights algorithm as a black box to adjust the prices and then basically greedily playing the online algorithm. Okay, any quick question? Yeah, so, okay, now I'm not sure about the ordering of the slides. Yeah, so, okay, good. Yeah, so here comes like the algorithm. Now the algorithm that I was describing. The algorithm we have right now is this multiplicative weights algorithm where we want to say that in each round, I ideally expect every resource to be B over N consumed. If you are consuming more or less, accordingly, I want to adjust the prices. And the way I define multiplicative weights, this is precisely what multiplicative weights also does. Like you have all these experts, you have M experts. Each expert is getting some reward between plus minus one. So what I'll basically say is in each round, the reward of an expert or of a resource will precisely be, I wanted you to consume B over N. If you consumed more, so then in some sense your price should go up. So my reward will be basically how much you consume a resource in a particular round minus B over N. So if you consume more, then in some sense this expert is getting more reward, its price should go up. If it's consuming less, then the price will go down. So let me say this in more formally. So use multiplicative weights algorithm. The price usually playing up to some scaling factor. It will basically be opt over B, this is some scaling factor because price and value are not in the same units. Like yeah, like budget consumption is at most B, opt is summing up to opt, like value. So you have to scale this opt over B factor to set the units same. Yi is what the multiplicative weights, the distribution it was playing over experts. And in each round, the reward that I will send to any expert. So in the ith round, the reward vector will basically be how much I consume. This AI is also like a m-dimensional vector. So each resource, how much I consume, minus this B over N. So again, the intuition to keep in mind is, first for our pricing problem, we wanted to say that, okay, you should be consuming B over N. If you're consuming more, then the price should go up because it seems like people are buying you currently more than what they should be. On the other hand, if they're buying you less than B over N, then the price should go down. And that's also captured in the multiplicative weights world by this reward function, which is how good this expert is looking. Experts correspond to resources. So I'm basically just going to use the multiplicative weights as a subroutine where the reward of the expert, any jth expert, will be precisely how much I consume this resource minus B over N. Question, yeah.
So how should I understand an expert use? Just a fixed price each round, that's one expert.
How should I understand what?
An expert in this context.
Yeah, so in this context, the expert is every resource corresponds to an expert. So you have M resources, M experts. And yeah, so yeah, okay, let me maybe I think repeat this. So you have M resources. Every resource corresponds to an expert. The experts algorithm is going to give me a distribution over these experts. It's a distribution that sums up to one. I'm going to translate that distribution into a m-dimensional price by multiplying that distribution by a scalar, opt over B. That's my price. So it's now a m-dimensional vector. These are the prices that I will offer to my ith request, like the next request comes. The ith request is now given these prices, it's just going to take the best action, like the greedy decision, because like it depends. These are the prices that's offered to this ith customer when they walk to the grocery shop. They are going to take whatever subset they want. Based on whatever subset they take, each resource has been consumed to some extent, maybe zero. This consumption vector, I'm going to give it as a feedback to my experts algorithm. The experts algorithm, yeah. So basically the jth expert, which corresponded to jth resource, its feedback is how much you consumed this resource, this jth resource in this round, minus B over N. So that's the entire setup. Okay, and those of you who might have seen like online packing, like packing LPs offline, how to solve them fast using multiplicative weights. Yeah, the ideas are very similar and inspired from there. And yeah, so that's the entire algorithm. And yeah, so roughly the reason the M factor gets improved to like a log M is because you have M experts. And in the experts problem, you only have logarithmic dependency on the number of experts rather than linear in M or something. Perfect. So yeah. And yeah, so I can maybe any question? Like, I mean, otherwise I guess quickly show how the analysis goes. I mean, yeah, I'll maybe not stress too much on the analysis. So roughly the idea is like, okay, algorithm can be written as sum of the values, that's by definition, up to some stopping time tau. There's some time when your algorithm might run out of one of the resources. Beyond that, of course, your algorithm stops, it doesn't do anything. So tau is the first time your algorithm halts, like before it halts. So I'm going to add and subtract some terms. Like, okay, like long story short, what I want to say is the analysis is pretty short. It will fit in a single slide. Somewhere you have to use, like, there are just two properties potentially to use. I mean, there's nothing more to use. One is the fact that I'm running a greedy algorithm. I offer a price. I always take a greedy decision. The other is I have to somewhere apply the no regret property. I mean, that's in some sense the only thing that we know which is non-standard about this problem. And that's precisely what happens. So there'll be like a couple of inequalities. One inequality will follow from the greedy property. One inequality will follow from the no regret property. And that's, yeah, I mean, let me just, yeah. So that's the entire analysis. What turns out is the analysis is, okay, you start off by some algorithm, apply the fact that you're running a greedy algorithm. So whatever your algorithm made the choice at the any ith step, instead, it could have chosen the optimal action. That was also an option, but you chose some other thing. So this greedy step, that's the greedy inequality. And then you have to apply somewhere the no regret property with respect to like, yeah. So I mean, let me not go over this. I think it will take more time to digest. Uh, yeah, so the entire analysis is pretty clean. And yeah, I mean, it took people quite some time to come up with this clean analysis and understanding for this problem. But it's like a very powerful result. It tells you so for online resource allocation for IID requests, like independent and from identically from the same distribution, we just saw like two algorithms. First is the approach where you kind of ignore the first epsilon n of your request, and then some kind of an LP dual prices, some fixed prices. That naively gives you m over epsilon cube. You can update it log times to improve it to have something like m over epsilon squared. That was the first approach. The second approach is via this multiplicative weights method, which gets you exponential improvement in the number of resources from m to log m over epsilon squared. And at a high level, the idea is that whenever we are playing these prices can be thought of as some kind of experts playing some distribution. So each resource can be thought of as an expert. You can use this as a subroutine. So yeah, and the algorithm is literally the precise algorithm is just this. Each round, I set up a price. I see how much my resource gets consumed. If it's more than B over N, then I increase the price. If it's less than B over N, I lower the price. B over N is the expected number, I mean, in the optimum because there are B in total. So in each particular time step, I expect roughly B over N resource consumption. Any questions? Good. Yeah, I mean, so like, yeah, again, as I was saying, I would highly encourage you first to understand multiplicative weights in more detail. And once you get comfortable, like it would be good to understand how multiplicative weights can be used to solve linear programs, even like packing linear programs. So this is known classically that how to solve offline linear programs fast using multiplicative weights. So how to get like a 1 minus epsilon approximation to an LP, to solving an LP. Using multiplicative weights, how to quickly do that. But what this is showing is that you can even achieve similar guarantees online. I don't even need to give you the LP upfront. The LPs it's gradually being revealed. And still you can apply this multiplicative weights machinery to achieve similar things. Okay, so if no questions, then maybe I'll quickly talk about how you can go beyond identical distributions. So till now I was assuming that you have these n requests coming for m resources, but these were IID, in identical distributions. Turns out you can also work about similar things for independent distributions, unknown even. So unknown distributions, independent distribution, they in general can capture like arbitrary adversarial input. So what we'll need is that although these are unknown distributions, I'll need at least just like one sample from each distribution, and that will suffice. Okay, so I'll maybe, just quickly mention this. Like, I think, I don't have time to go over details, but like the setup is that, again, these n requests, ith request comes from some unknown distribution di. The goal is, as always, to maximize my total value subject to the budget constraints. Total value minus the resource consumption. And one could ask questions like, for instance, like how many samples do I need from the underlying distribution to get a 1 minus epsilon competitive algorithm? Okay, and can we achieve this using a posted pricing algorithm? Good, and you need some kind of samples, like something in, so in the IID case, when the distributions are also identical, I could kind of learn as I go because samples came for free. I can always ignore the first epsilon fraction of the input, use this as samples, and then just optimize for the remaining 1 minus epsilon fraction. That would, it doesn't hurt me too much. It only hurts me epsilon opt value. For non-identical distributions, you cannot use this because, the first few distributions may have nothing to do with the last few distributions. They have nothing to do with each other. So in some sense, one needs to be given some additional information. And that's the reason you need at least maybe one sample or two samples. So this is some result that I guess appeared just last week at Stock with some students. Like, so we showed like you can get a 1 minus epsilon comparative algorithm even for non-identical distributions, as long as each budget is again like some log over epsilon squared or something like this. So either you give me like polylogarithmic number of samples, like from each distribution, you give me polylog number of samples, then I can get you like exactly this. Or turns out you can even like one sample from each distribution also suffices. But then currently we can get like polylog over epsilon to the 6. So we are currently not able to get like 1 over epsilon squared. But at least the dependency on m, the number of resources, is still logarithmic. So there's some, it's not ideal, but like only a single sample from each distribution. You don't need to know more about the distributions. Just single sample from each distribution suffices to get a 1 minus epsilon approximation. Is the statement of the result clear? So when I say one sample, it basically means one sample from each of these n distributions. These are independent and non-identical distributions. So I give you the sample upfront and then use the sample to learn whatever, like play any algorithm that you want. And it's also a posted pricing algorithm. So it's not just an algorithm, it's a posted pricing algorithm. Hence, it has some implications to auctions. It also has implications to robustness. Turns out this algorithm is also quite robust in the sense if there are like some noise added to the system and like there are many formal ways of defining robustness, it achieves quite a few of those properties. Okay, the high level idea is that we need to come up with a good pricing algorithm, like the way how to update prices. So what we end up doing is roughly the following. So remember in the IID case, overall I had to consume B budget. And because requests, everything was identical, per time step, I expected to exactly consume B over N resource. Like overall, I'm consuming B resources and there are N time steps. So each time step, I'm consuming B over N resource. For non-identical distributions, this is totally not true. There might be some dumb requests where you don't consume any resource. There might be some requests at time steps where you have to consume a lot of resource. This is precisely what we'll try to learn. So what we'll use is that use the single sample or multiple samples to estimate until every time step roughly how much budget I should have consumed. So by half time, should I have consumed maybe 10% of my budget? Should I have consumed like 90% of my budget? So you can use this single sample or like these multiple samples. So the trade-off, like all these 1 over epsilon squared and 1 over epsilon to the 6, this is coming precisely like, okay, how well can I estimate this using my single sample or multiple samples? So the idea of the algorithm is first estimate how much is the expected budget consumption by the optimum algorithm. I don't know the optimum algorithm, but I want to roughly estimate. the optimum solution, how much time, how much budget it should have consumed by, let's say, half time, or like ideally by every time step. And then use these estimates to update my prices. And then the pricing algorithm would kind of be obvious. Like by halftime, I expected my budget to be consumed like 10%. But for some resource, if I've consumed it like more than 10%, its price should go up. If, if the price, yeah, if I've consumed less than 10% of a resource, then the price should go down. The intuition is the same. I mean, the details have to be worked out. I mean, okay, how exactly do you, how quickly do you increase or how quickly do you decrease? But that's precisely the algorithm. So it's going to be the posted pricing algorithm of the following kind. And we call it the exponential pricing algorithm. Like roughly what we do is we start off with some initial price, and in each time step, the new price will be the old price times some exponential function, which is like delta is some scaling parameter, doesn't matter. It's the difference of how much you consume minus, ideally, I want to say, what is the expected consumption in the ith time step. So had I known the distribution, there's going to be some expected consumption by the optimum decision, optimum LP solution of a particular resource J. Like let's focus on a particular resource J. Had I known the distribution, there's some expected consumption by the ith request of the jth resource. So I want to basically say that if your consumption in this current time step is more than the expectation, then the price should go up. If it's less, then the price should go down. The way I'm going to update it is via some exponential function. And that's precisely that's happening. In reality, I won't have this expectation exactly, but I have some estimates, like because of my single sample or multiple samples, I have some prefix estimates, budget consumption. You can translate that into some estimates here as well. And yeah, that's the underlying idea. And yeah, so one can make this formal to argue that actually, so we don't use exactly multiplicative weights, but it has connections to online learning as well, this kind of a pricing algorithm. Let me skip the details, but the analysis is again, like, I mean, somewhat similar. Like, yeah, it requires some more care. But yeah, the details are not so important. So long story short, so main things that we learned is, first of all, what is online resource allocation, why it's very useful and algorithmically powerful. For known distributions, things are quite easy. You can get a 1 minus epsilon approximation just by doing LP rounding, uh, as long as the budget is like log over epsilon squared. But turns out you can also get similar guarantees, poly log over poly epsilon, even when the distributions are not identical, even using exponential, even using prices by like what we call exponential prices. You have to use some kind of a low regret, like, or the no regret property, the properties of things like the online learning for multiplicative weights. Some open questions I guess we have are, so we achieve all these guarantees currently using dynamic prices. Like each round, the prices are changing. We don't have currently a good understanding of what can I achieve using static prices. So like currently I'm saying like each round, whenever the next request comes, I'm going to literally update the prices at the grocery store. That's not what you can really do in practice. Like ideally you want the prices not to change too much. So this trade-off we don't understand very well right now. Like how, like the trade-off between how many changes I do versus how much value I can get. So that's one thing to understand. There are also questions of the current, like about sparsity of the problem. Another question that I guess it's not here is about like currently with single sample, like we can only get like polylog over epsilon to the 6 budget bound instead of, let's say, polylog over epsilon squared. So this again, yeah, we've made some progress, but yeah, the tight bounds are still quite open. Okay, yeah, I think that's where I'll end the technical part. Yeah, so I'm happy to take questions. It's how much time do we have? Okay, we have 10.